Hello, can you hear me?
Sajid, we can hear you.
Okay, thanks. Okay, yeah, okay. Good. So where were we? So what we did was we okay. So let's recall. So we have given a point set P, and the goal is to calculate its core set. Okay, we want to calculate its core set with respect to the function CMEB. Okay. So rather than keep writing CME, we just call it C. Okay, and where CP of X is defined to be max over all Y in P x minus Y. Okay. Yeah. So with respect to this cost function, okay, so we want to calculate a core set given the set P. Set like this P. Okay. And what we did was we first calculated an square root epsilon net of vectors v1 to vt. Okay, for each vector vi, we calculated the point y in P that has the we find the point y which has the maximum dot product with vi, and the point another point that has the minimum dot product with vi. Okay, and we do it for each vi. We get 2 points from P. Okay, and taking union of all of these points, we get the set S, and we want to show that set S will be our core set. Okay. Okay, so in terms of size of set S, we are in good shape. Okay, so it is 1 by square root epsilon to the power d minus 1. Okay, the only thing we have to show that the core set property is satisfied. So that we have to show, again, you remember the definition was for any extension of P, it should that approximation guarantee for the thing should be satisfied. So let me write it. So let T subset of RD be an arbitrary extension of P. Okay, then what we want to show CP union T of X is less than equal to 1 plus epsilon CS union T of X greater than equal to C S union T of X. Okay, this thing we don't have to prove. It is already given because the function C is a monotone function. So what do I mean by monotone function? So C is monotone if CQX is less than equal to CPX for all Q subset of P. Okay, which is the case here, right? I mean, that directly follows from the definition. Okay, it's a monotone function, so we don't have to worry. Okay, good. So the main thing that we have to prove is this part. Okay, right. So and by the way, this equation should be true for all x. We want to show that for all x, I should write here for all x belonging to RD. Okay, good. So let's see. So let's look at this thing CP union T of X. Okay, so let this be equal to Z minus X for some Z belonging to basically Z equal to argmax of Y belonging to P union T. Yeah, if I substitute this Z here, we will be okay, right? So what am I? So why am I writing like this? This is basically saying there exists a point Z which is farthest from X in P union T. Okay, and let's call that point Z. Okay, good. Okay, so you have this X, you have this point Z. Look, let's look at this vector. Okay, good. So we know by again our construction that there exists a VI for which this angle will be at most square root epsilon, right? VI belonging to V. That's just by construction. Is it the case or not? Just direct construction, right? This vector xz, there will be a vector vi which will make a small angle with this. That's it. Okay. So let's say project z on this. Let's say get z prime. So let me write slightly different here. Vi belonging to v. Okay, good. Right. Okay, so even before I do this, okay, so let me do this later. So like suppose z belongs to t. Okay, if z belongs to t, do I have to show this? Like basically, does this follow directly? See, the point that is farthest in P union T is in T, then there's a point that is farthest from X in S union T. S is a subset of P, right? Will also be that same point, right? So if Z belongs to T, we actually have nothing to prove. Okay, then the result holds. Okay, so we can assume. That Z belongs to P. Okay. Okay, so for that Z belongs to P case, again, let's go back here and see what is happening. So I am looking at this vector xz. I find this vector vi from my net, okay, and I project on this vector, okay. This vector vi, I'm making it pass through x again, and I'm projecting it on this vector starting big vi that I'm just like anchored at x and projecting z on it. So we get z, right? Good. Okay. What can we say about this? Does there exist another vector which is further than this in P? See, the way we have constructed my set S, okay, there will be a vector whose projection will projection on Vi will be at least this. Because for each Vi, I calculated I had two vectors, right, in S. One that makes the largest dot product with Vi and one that makes the smallest dot product with Vi. Okay. The one that makes the largest dot product, the length of its projection will be more on vector Vi, right?
Right.
It's okay?
Yeah.
Okay. So let's do it. Okay. So can I write this? But this is direct, no? Nothing to. Okay, so let's look at this equation closely. This is and cos of the angle between Vi and exit. Yeah, this is greater than equal. So this angle is obviously less than equal to square root theta, square root epsilon, because I have taken a square root epsilon net, right? So I can write, and then we use the fact that bigger projection is. Okay. So now let's look at. I'm just using. Okay, so I mean, like this might look something. I'm just following this direct properties that I've used. Okay, nothing fancy is happening here. So basically, I use this to show that C of P union T of X is less than equal to C S union T X by cos of square root epsilon. That's it. This is what I need. Just I play around with those equations and you just get this. Okay. Right. Okay. So now we know like cos square root epsilon. Taylor series tells you what? So it's 1 minus epsilon by 2 factorial plus epsilon square by 4 factorial minus epsilon cube by 6 factorial, like this, right? And this is greater than equal to 1 minus epsilon by 2, right? Again, substitute this here. So what is that? C of P unity x, okay, is less than equal to C S unity x by 1 minus epsilon by 2. And this you can just show is okay. And so this completes the proof. That's it. Is it clear? So it's just some equations you have to manipulate. Okay, it's nothing fancy happening here. The main idea is the construction of the set S. Okay, using the construction of this set S, you just have to go through this like few steps. Okay, and then the result will follow. Okay, so this is good. So, but looking at this proof, can we like say that okay, can I maintain this epsilon 1 plus epsilon code set over a data stream when the points are coming over a stream? Right. So if I directly use the result and the theorem too, I would have got a code set of size how much? We wrote somewhere, no? Code set of size like yeah. So like just knowing that there exists an epsilon net of size square root epsilon to the power d minus 1 and the disjoint union property, the code set size we said was something like log n to the power d plus 1 by 2 by square root epsilon to the power d minus 1, right? But see, the way we have done the proof, actually I can maintain this code set on a stream without without needing this. This is not required. I can pre-compute the epsilon net, a square root epsilon net beforehand. Okay. And then for each vector Vi, I will be just be maintaining two vectors that means for the largest that has a maximum inner product for the currently the set of points I have seen, and the smallest inner product for the currently the dot product for the set of points that we have seen. Okay. So like this thing, I can maintain over a data stream for each VI. And how many VIs do we have? It's square root epsilon 1 by square root epsilon to the power d minus 1. Okay. So I can just like the log term is actually not required. For minimum enclosing ball problem, this log term won't be required. Okay, so that's the interesting thing about this result. A proof of this result. But the idea, by the way, the proof, this proof is exactly inspired by Dudley's. The proof for approximating convex body also goes exactly, almost exactly along these lines. Okay. So with slightly careful you have to be, but not much actually. Okay. So this was the thing I wanted to do in part 1. So let's go to part B and see some applications of Coresight in CG. Okay. I mean, this kind of merge and all these properties are something that are not that much used in, like, its full strength are not that much used in CG. Okay. In CG, the question is like time complexity. Space complexity is not something we are that interested. Okay. I mean, obviously we want to store few points because that will help us get a faster algorithm. Okay. Okay, good. So let's see. So by the way, anyone has any questions for this? So if you don't remember anything about the proof, you don't worry, you can reconstruct on your own. But the only thing you remember is how to construct that set S. That is the most important thing in the proof. Okay? The way we construct the set S, that is the main idea in the proof. After that, you just few lines of manipulation will give you the result. Okay. So any questions? So I move to part 2, part B.
Yes, sir.
Okay. Okay. So let's look at it. So here in this setting, I have the points. Okay, so there is no coming over a stream or anything. I have this set of points. Okay, n points in RD. Okay, and I want to compute the minimum enclosing ball. Okay, what should be your algorithm for computing the minimum enclosing ball? Let's say I want to compute the minimum enclosing ball. What will be your algorithm? Okay, one way is to formulate an LP actually. I mean, not LP, it's a convex program, but like with constraints that are linear constraints. Okay, the way to think about it is the following. Okay, so you have been given as input this set of points. Okay, you want to, what is the output? A center and a radius. Okay, where you have to minimize the value of R, and the center, if I draw a ball of radius R around the center, all your points should be inside. And you want to find a ball, you want to find a particular center that minimizes this value of R for containing all the points. Yeah, so that is a problem. Okay, so how should we formulate it? So one way to think about it is, okay, so for all I do the following. These are the things I want. Pi minus C square is less than equal to R square. Okay, this for all I 1 to n. Okay, so let's slightly simplify this. So we get plus, let's say here we get inner product. Okay, here the variables are C and R. Okay, good. So let's rewrite it slightly more. Okay, so let me write R hat to be R square minus C square. Okay, so what do we get as an equation? We get, let me write it. So minus 2 pi c less than equal to r hat and minus pi square. Okay, and we have like, this is like n equations like this, like I goes from 1 to n. Okay, and I want to minimize what? Minimize the value of r hat plus c square. Okay, so let me write it. Minimize this subject to the condition that minus 2 PIC less than equal to r hat minus pi square, and you do it for all I from 1 to n. Okay, so this is like a convex program. Okay, so the constraints are, your constraints are linear constraints. Okay, and this is a convex function. Okay. Okay, so yeah, so this is something. So in optimization class we learn this. Okay, so like how to solve this kind of thing. This is like a standard technique for it solving this. This is like this is like basically what is called prune and search technique. Okay, prune and search technique. And search technique is there to solve problems like this. Which is good. Okay, but what will be the complexity? The time complexity for these are not that good in terms of d. Time complexity turns out to be order. So let's say I don't hide the complexity in terms of d. It's something like d to the power d times n. Okay, which is not good. Right? So okay, so like computing minimum enclosing ball doesn't scale nicely as we go in higher dimension. Okay, if I use this approach. Okay, so there is a randomized algorithm also to compute this. That is a like one of like very important results. A randomized algorithm for computing minimum enclosing ball. I don't want to give the algorithm. It's very nice. It's what is called, the technique is called randomized incremental construction, RIC, randomized incremental construction. Okay, but that also has like not good time complexity. So the time complexity. So since a randomized algorithm, it's an expected time complexity. So expected time complexity turns out to be something like order n times e to the power, what was it, square root, or I think it is some square. Okay, order square root d log n or something like this. Okay, so again it's kind of like exponential in d. Then it's exponential in square root d. Not good. Okay, so okay, so when we have this like horrible time complexity of computing like exactly minimum enclosing ball, and even in like randomized algorithm also it's not that good compared to the deterministic one. Okay, the natural thing is, I mean, see that this one we can think of is maybe slightly better with some range of values of d. Okay, but still bad. Okay, I mean then, like, so a natural thing to do is like, okay, so I don't want to exactly compute the minimum enclosing ball. I will be happy if I get an approximation. Okay, so what is the goal? So the goal is the following. So goal was in like CG was the following. The idea was, okay, it's hard to compute. It's like time complexity wise not good to compute like minimum enclosing ball. So do one thing, find a subset Q of P such that, so let me write like this, MEB be the radius. So MEB of Q is a good approximation in terms of epsilon of the minimum enclosing ball of P. Okay, this is where the motivation for Coresight came. One of the motivations for Coresight came. Okay, there's another notion of kernels. Okay, but we don't have to go to kernels. But this is one of the motivations. Okay, so like, okay, I mean, exactly the minimum enclosing ball computing is not nice in terms of exact complexity, time complexity. So okay, can I get a more efficient time complexity algorithm, but I get an approximation. Okay, I lose out on the optimality, exact optimality, but okay, but time complexity wise it will be much better. Okay, so more like if I want to write it tightly, so like minimum enclosing ball of P should be something like less than equal to 1 plus epsilon times minimum enclosing ball of Q. Yeah, you want something like this to do. Okay, and you want size of Q to be as small as possible. Here the motivation was not for all extensions these properties should be hold, it is a function to it, nothing. I mean, like, just minimum enclosing ball I have to compute, time complexity exactly computing is bad, can I approximate it more efficiently? That's it. That was the idea. Okay, is the motivation clear why we want to do this? Okay, so how should we go about doing this then? Okay, so there were like number of algorithms. So there was a like initial result. I forget exactly the references now, but like one there was something like d by epsilon square bound. Okay, they showed that okay, given any set of points p, there exists a small set of points of size d by epsilon square up to some constant. Okay, whose minimal enclosing ball will be a good approximation of the minimum enclosing ball of p. Okay, so these are like Coresight sizes. Okay. Okay. So after like some series of work, finally there was a proof from the book uh, by Clarkson and okay, what is the other person's name? I don't know how to pronounce Badu, something like this. Okay, okay, it's like a just a half page thing, and they showed that okay, it's a very simple algorithm to compute this set core set of P, whose size will be 2 by epsilon. For the size won't be even dependent on D. Doesn't matter in which dimension you are in now. Okay, it will be independent of the dimension. Okay, and it will be 2 by epsilon. And the way you do it is so simple. It's so simple. I just tell you the idea now. It's just like unbelievable. The analysis is also not that hard. Some slight manipulation, but the main idea is just super simple. Okay, so what's the algorithm? How to construct this core set of size 2 by epsilon? Okay, so you have this set of points, right? P1 to Pn. Okay. Okay. What you do is you start with an arbitrary point. So let's say P1. First, you build a set Q incrementally. So in Q, you first put the point P1. Okay. Okay. What will be the minimum enclosing circle for P1? P1 will be the center and the radius will be 0. Okay. So let me write it like this. Q1 be P1. Okay. Let's say. Okay. So this minimum enclosing circle, that center will C1 be P1 and the radius R1 is 0. Okay, good. So let's say like this, I have built till Qi. I have included P, so let's say P1 or P2 or something like this. Some set of points. Okay, so let me not write P, but I say Q, Q1, Q2. Okay, these are the points, but these are all subsets of P. Okay, so let's say the minimum enclosing circle for the set of points Qi be center be Ci and the radius be Ri. Okay, so you have this center Ci, radius is Ri. Okay, and you have all the points of Qi are inside. Okay, So some points of P are still maybe outside. Okay. Okay. I will increase the size of the set. If suppose a ball centered at Ci of radius Ri, if includes all the points of P, then we are done. We have nothing to do. Okay. Suppose some points of P are still outside the circle. So okay, I have to modify this new circle, right? I will be modifying the set Qi. What I will do is I will find in P the point which is furthest from Ci. So let's say this is the point is furthest. Okay. This is the point that is furthest. So this will be my Qi plus 1. That is furthest from Ci. And I will make one to be Qi union Qi plus 1. Okay. What Clarkson basically showed is you do this procedure T times and stop. And you will be done where T is equal to ceiling of 2 by epsilon. That's it. That Qt will be your core set that you are looking for.
So this is like a greedy algorithm, right? I mean,
Greedy, it's like an algorithm that I could have asked you to implement in like first year, like in your school,
yeah,
right? I mean, there's nothing,
exactly.
right? I mean,
So
there's
I
nothing
mean,
algorithm.
when we do the set coverage problem, I mean, yeah, I mean, it's not totally similar, but there also we do that. We choose the
Yeah, yeah.
farthest number of points that is outside, and
Further,
we, yeah,
yeah. So this we do. See, this similar idea is also there for like to get a two approximation for K-center problem. So there is a clustering problem for K-center. Okay, there is an NP-hard problem in general. Okay, but there is a technique of what is called you build your, you have to find this K. Okay, so I mean I don't want to get it. So there's again there is a greedy algorithm for that. I mean this is along that line only. That's it. Okay, and this will give you basically your core set. Okay, so let's see if I have some time I will give the proof for this. But this algorithm also has like a so this will give you a core set. Okay, good. In terms of core set, it is nice. Okay, so we should compare, right? Okay, so we already saw a core set of size 1 by epsilon to the power d minus 1 by 2. It had a bad constant in terms of d. Okay, here it is independent of d. It's just 2 by epsilon. See, I mean, this actually kind of outperforms this one in dimension 1 and 2 actually. 1 to there is nothing to do, but in 2. In 2, this gives you like, okay, the core set is of size 1 by square root epsilon. Okay. But the interesting thing is this result doesn't scale in high dimension. Okay, it becomes bad in terms of as d grows. This scale, there's nothing scaling. The bound is independent of d. And anyway, the boundary is independent of n here also, but it will be independent of n in the second case. Okay, good. This is one. There is another algorithm actually. Okay, which is also super interesting. That again in the same paper Clarkson did. Okay, so how many have you heard the term like gradient descent? Okay, is it
yeah,
like it's a term gradient descent? No, it's all rage, no? So machine
yeah,
learning, everyone doing convex optimization. Okay,
yeah.
you ask someone from English language, they also know what is gradient descent. No? So gradient descent is what you try to move closer towards an optimal solution, taking small steps, right? Okay. What Clarkson did in this paper, in the same paper again, Clarkson Bodu, was they built another algorithm for minimum enclosing ball, which will be a good approximation. That is along the line of gradient descent. What it will do is almost in the same way. So you start with some arbitrary center. So here now, so the goal is to calculate the center. So right, so you have this set of points. Okay, So you have like you start with an arbitrary point and call it the center of this set of this. That's it. Okay. My pen again, the charge I think is the problem. Okay, so you draw a circle here centered at this point. Okay, that includes all of this. Okay, and obviously this is not an optimal center. Okay, what you do is, let's say at the ith point of your iteration you have this. From Ci, calculate the point which is the farthest. Okay, let's call this Pi plus 1. Okay, you move your Ci in direction of Pi plus 1 by how much? By distance between Ci minus Pi plus 1, this distance by I plus 1. From here towards this, I will be moving by this much amount. And that will be my new center, I plus 1. Okay. I will do this step 1 by epsilon squared time. Okay. I will get 1 plus epsilon approximation for minimum enclosing ball. This is also, again, extremely simple, right? I mean, in terms of complexity and calculating, I mean, this is like, yeah. So, okay. So I won't give you the proof of this. The proof of is exactly almost along the same lines as the proof of this one. The first, the Coresight proof is what I will be giving now. Okay. So this paper by Bodu and Clarkson, this has this like 2 small gems, and both like proofs are like just like quarter page. Okay, something like this. Okay, so let's see. Let's try to prove that Coresight result. Okay. So let me write it as a theorem. The theorem for MEB, there exists a Coresight 1 plus epsilon Coresight of size at most 2 by epsilon. Okay, this is what we will be proving. Okay, good. So before I prove this, I need one small technical result. Okay, so just let me think just 1 second to prove that. Okay, good. So yeah, so let me do proofs by picture. Okay, for the timing. So you have a minimum enclosing ball for some set of points P. Let's C be the center. Okay, we are, by the way, we are working in RD. Okay, I mean this result is interesting in RD only, not interesting if you are looking dimension D equal to 2. The other result that we saw, that will be better than this, D equal to 2. Okay, so okay, so we will use this this small technical thing. Okay, which is that, let's say, so does everyone know what is a half space? Okay, so you know what is a hyperplane, right? Okay, so hyperplane, if you don't know, so hyperplanes are basically generalization of lines in R2 to RD. Okay, these are basically linear equations. Okay, equations like this: summation ai xi I equal to 1 to d equal to some constant b. Okay, these defines hyperplanes in RD. Okay, these are basically generalizations of lines in R2 to RD. Okay, and what is a half space? Half space is basically, rather than having this equality, you make it into an inequality like this: summation ai xi I equal to 1 to d less than equal to b. set of points that satisfies this equation, where the ai's and b are constant, variables is xi's, okay, set of points that satisfies this equation are basically half planes, okay, in RD. Okay, so the idea, so the one technical thing that we need is you consider any half plane, okay, that contains your center for the minimum enclosing circle, minimum enclosing ball for your point set P. Okay, it contains C. Okay, then it will also contain there will be a point in P that will be contained in that same half plane, but will be on the boundary of the ball. Okay, is the result clear? What I'm trying to say? So look at it in terms of R2. Okay, R2, you have this minimum enclosing ball for, let's say, some set of points. It has a center C. Take any line, okay, that cuts this circle. Okay, let's say C be on one side of this line. Okay, the side that contains C, if really C is the center of the minimum enclosing circle for this set of points, and okay, so then there will be a point in your point set P that will be on the boundary of the ball, minimum enclosing ball, and will be on the side of C with respect to this line, blue line. Okay, this is the only technical thing that we need to prove the Clarkson's result. Okay, is this the idea? Is the statement of this the thing that I'm saying is clear or not? Sorry, is it clear?
Yes, sir.
So think about in terms of R2. Okay, for the time being, if you can understand the proof in R2. Okay, so let's write the proof in R2. So D equal to 2 is what we are doing. Okay, the proof actually directly goes through for RD, and nothing fancy happens in RD. Okay, so let's do it for D equal to 2, this proof. Okay, is this clear? That if a half plane contains the center of the minimum enclosing ball, okay, then there will be a point in P that will be on the same side as C and will be on the boundary of the ball. Okay, that's the only thing we're using. Okay, good. So as we see, we were building this sets Q1, Q2, QI, QT with corresponding centers C1, R1, C2, R2, CT, RT. Yeah. So CI is the center of the minimum enclosing ball for the set QI, and Ri is its radius. Okay. Good. So let me introduce some more. So let R be the radius of minimum enclosing ball of the point set P. Okay. And then we define a few more parameters. Okay. So the parameter is, we define lambda I to be equal to your Ri by R, and delta I is equal to distance between Ci and Ci plus 1. So how much did your minimum center for the minimum enclosing ball moved when I modified Qi to Qi plus 1? Okay. Okay. So what is delta 1 value? Lambda 1's value in the first step? Can anyone tell me?
So 0.
0, right? What we will be basically showing is lambda 1 will become something like 1 plus epsilon. Okay, at the tth step. Lambda t will become 1 plus epsilon at the tth step. Okay, not t plus epsilon, but something. Okay, so it will become greater than equal to 1 minus epsilon, something like this. This is something we will be to prove. This will be to prove. Okay, but lambda 1 is 0 is nothing to prove, right? Q1 has just 1 point, right? Okay, so R1 is 0. Okay, good. So, okay, so let's say we are at the center Ci now. Okay, so we have this set Qi with center Ci, radius Ri. Okay, can we say that there exists a point Q in P such that distance between Ci and Q is greater than equal to R? If this is not the case, there does not exist any point Q for which distance between Ci and Q is greater than equal to R, you are already at the optimal point, right?
Yeah, right.
Yes, so there is a point. There is a point.
So there exists a point. Okay. If everyone is less than nothing to. Okay. So then can I write this? Just triangle inequality. It's directly triangle inequality, right? Again, nothing to do here. Okay, and this I can write as greater than equal to R minus tilde I. Okay, so this will also give me a recursion equation. It gives us recursion inequality. We won't get equation. We get a recursion inequality actually here. It's okay. Hello, can you guys hear me?
Yes, sir.
Hello,
we can hear
so
you.
the connection is getting cut. I don't know, from my end it's okay. Okay. Okay, good. So now the idea is the following. Okay, so let me think this 1 second. Okay, so if delta I plus 1 is equal to 0, okay, then the center has not moved, right? I mean, basically the new point that I have added, okay, is inside, right? The new point that I've added is basically inside. If delta I plus 1 is 0, okay, if the center, if say Ci and Ci plus 1 is same, then also I'm at the minimum enclosing. I've already found the minimum enclosing center for the minimum enclosing ball, right? Yes, no? Because Ci was the center of the minimum enclosing ball of Qi, right? Let's say there is no, if the center doesn't move, that means rest of the points of Pi is inside, right? So I'm at the, yeah. So we can assume again. So we can assume that 1 is greater than 0. So how did I define delta I plus 1 properly? Oh no, delta I. Delta I. So let me write it like this properly. Delta I is Ci minus Ci plus 1. Okay, and you can assume that this is greater than 0. Okay, good. Because this implies we have reached the center for the minimum inclusive ball, center for MEV. Okay, good. So what I do is the following. Okay, you have this Ci plus 1, you have Ci. Okay, take a, so we are doing it for the case of R2. Okay, take a line passing through Ci that is orthogonal to this line segment and going through Ci. Okay, segment is this orthogonal, this line should be orthogonal to the segment Ci plus 1 and Ci. Okay, this is okay.
Yeah.
Okay, good. So again, now look at the ball Bi, which is the minimum enclosing ball for the set Qi. See, this half plane again contains Ci, right? Okay, by the result that we already saw, there will exist a point P on the boundary on this side.
Yes.
Right? Okay. What is this radius? This radius is Ri. Right? So I can say that Ci plus 1 minus, let's call this point P. Okay. Ci plus 1 minus P, this distance is greater than equal to square root. See, Ri is nothing but lambda I R. Right? I can write, lambda I R square plus this distance is delta I square.
Yeah. Okay.
But see, the point P is contained in Qi plus 1 because the P is contained in Qi. Qi is a subset of Qi plus 1, right? Right. So what does this equation and this equation gives us? It will give us the following recurrence inequality. It gives us lambda I plus 1 R is greater than equal to max of R minus delta I, comma, is it okay? Just combining these two. See, I mean, this term is less than equal to Ri plus 1, right? Definition of Ri 1 is basically will give you this. Okay. And this is basically Ri plus 1. I've just written it like this because I want to have a recurrence on lambda I plus 1 and lambda I and delta I. Okay. This recurrence inequality is what I need. That's why I've written it like this. Okay. So I have, again, so let me rewrite this recurrence inequality more cleanly. I have something like lambda I plus 1 is greater than equal to max of 1 minus delta I by R, comma, square root lambda I square plus delta I square by R square. Okay. See, what do I want to prove? As I said, I wanted to prove a lower bound on lambda t. Okay. I want to prove lower lambda t is greater than equal to something. Okay. I will now prove that a lower bound on that by, so this is what I want to prove. I want to prove a lower bound this, which is this is what I want to prove. Okay. So what I do is now is with this recurrence, I want to minimize lambda I plus 1 as a function of delta I. So I want to minimize. So what we want to do, so let's write this as equation 2. We want to minimize lambda I plus 1 as a function of delta I. So how should I go about doing that? Any ideas? To minimize it, what I do is, as a function of delta I, I will try to find the value of delta I for which both of these are equal. Right? Because lambda I plus 1 is a max of both of these quantities. Right? The place where this is equal, this is the place I will be able to minimize lambda I plus 1. Okay? So just substitute this equal to this. Okay? If you substitute, what the value of delta I that you get is something like this. 1 minus lambda I square r by 2. Okay, this is from my notes, so again, I don't want to evaluate it, but basically, to do this minimization, I just have to take this equal to this. That's it. Okay. So you get, again substituting back, you get this recurrence. Lambda I plus 1 is greater than equal to 1 plus lambda I square by 2. Okay. What you do is you have to solve this recurrence inequality. Okay. There's a standard way of doing it, change of variables. I don't want to go now and do this. But what you can show is this would imply that lambda I will be greater than equal to 1 minus 1 by 1 plus I by 2. Again, this is not obvious from this. This requires some number of steps. I'm just writing it from my notes. Okay. But this recurrence inequality will give you this. That's it. Okay. Now just substitute at what point this, for what value of I, this will be greater than 1 minus epsilon. Okay. And you will get your equation. That's it. So this will complete the proof. Is everyone still with me?
Yeah.
Yes, sir.
Yeah. So this is, by the way, there is a standard way of manipulating this kind of recurrence inequality. Okay? It's not that hard. Okay. But the main idea of the proof is actually the main idea is that algorithm. Okay, that simple algorithm is the main idea. Okay, so you can show that if t becomes that 2 by epsilon, this value will become lambda t will be greater than 1 minus epsilon, and that is what you want to prove. That's it. Okay, good. So this is nice. Okay, but what will be the time complexity now? Okay, so with all said and done, see, one of the main reason for doing all of this was complexity was something like this to compute minimum and closing circle. But even after doing all of this, if the time complexity still remains this, what am I gaining? I'm getting nothing. I'm losing out on quality, getting nothing on time complexity. Okay. So what will be the time complexity of this algorithm? See, you will be calculating minimum enclosing circle for 1 by epsilon many sets. Each will be of size at most 2 by epsilon many sets. Each will be of size at most 2 by epsilon, right? That is one time complexity. Okay. How much will that incur in terms of time complexity cost? It will be d to the power d times 1 by epsilon square, right? Okay. But we also need to do one more thing. We have to calculate the farthest point from the center. Okay. Right? That will incur, and we have to do it how many times? 2 by epsilon times. That will incur the cost, this. So this will be our complexity. Okay. Which is actually much better. Okay. I mean, this constant in terms of in front of 1 by epsilon square is much better than having it in front of n. Okay. So we are losing out on guarantee. Okay. I mean, for sure. But we are not like, we are really gaining in terms of time complexity, right? By the way, this MEB, even though the problem sounds extremely trivial, has number of applications. Like basically, this technique, using this Coresight idea, you can get a Coresight for K-center problems, okay, which are like difficult problems. Clustering K-center problems. These are like type of clustering problems, for geometric clustering problems, okay, and you can show that there exists like a fast algorithm using this Coresights, okay. Okay, good. So this is where I want to end. I want to say a few more things. One is like code. This is just I just basically skimmed the surface of this area. Okay. Coresets, again, because of all machine learning thing, has been like used a lot now. Okay. And it has number of applications in machine learning. If you just type Coreset and machine learning, you will see number of really interesting surveys. So Saket, is it possible for me if I forward you those references that you can forward it to the students? Saket, are you there? Fahad, anyone? Okay, I will talk with Saket about this. Okay, so I will forward the references with like applications of this Coreset technique to machine learning, learning theory, and many other places. Okay, and which I am sure he will forward it to you guys. Okay, that's it. Any questions? This is what I wanted to cover. No questions? Okay then. So thank you for your patience. So I'm ending the class now then.
Thank you.
Yes, sir. Thank you.
Okay, thank you. So bye.
Hi, Arjit. Are there any questions from these people? No? Okay. Session ended. Okay, okay guys. Okay, so see you all people tomorrow at 11 o'clock.
Yes, sir.
For the last two lectures. Okay, bye-bye.